You've seen how the normal curve can be used to approximate the binomial probability histogram. But the normal curve can be used to approximate many other probability histograms as well, and we'll start with a very simple one, an example that we have studied to death, and so I'm going to bring it on with a big bang right like that. It's the total number of spots in 200 rolls of a die. I know it's dry, but you also know that it is a simple example. It's just to illustrate the basic technique, and then we can get to things that are more interesting. So we've got the sum of 200 draws from the box 1 through 6. We know the average of the box. We know the SD of the box, which we calculated longhand using our old methods from 2.1 x. And we know that we expect the sum to be 700, give or take 24. And so now we want to look at the probability that the sum is in various ranges. So what if I asked you, what is the chance that the sum is in the range 700 plus or minus 24? Well, it's center plus or minus measure of spread. If the distribution were normal, you could just answer that, couldn't you? So why not live dangerously? Let's pretend it's normal. Suppose the probability distribution of this variable is roughly normal with the correct mean and SD as we calculated. What is the chance that it's in the range 700 plus or minus 24? Well, if it's normal and you're looking at center plus or minus one measure of spread, then the answer is roughly 68%. Done. That was easy. Similarly, you can find the chance that the sum is in any range. So what is the chance that it's greater than 750? Well, you've got a curve that is centered here with this spread. You want the chance that it is greater than 750, so you better convert this 750 to standard units. So you find your z, 750 minus 700 over the measure of spread, and that's 2 and a bit. Those of you who are sticklers for method might say, you know, it's greater than 750, that the next bar therefore is 751, which starts at 750 and a half. This half is the width of half a bar because these bars are 1 unit wide. And so this is our old correction that we did when we had the binomial histogram where there were bars at consecutive integers. And you can do that correction and you're not very different from what we had here. And so what is the chance that you want? Well, you want the area to the right of this point under the standard curve, and that is roughly 1.85% using your normal curve applet. Done. Easy. Is it? Well, it's under a pretend. It's pretending that the normal approximation works. So the natural question is, well, is the approximation any good? And let's take a look at what your text has to offer in this regard. So your text has an applet that will let you enter any box that you want. Well, I think it has to be of some degree of simplicity, and I'm going to enter the die 1, 2, 3, 4, 5, 6, and it allows you to take a sample and calculate the distribution of the sample sum, and I'm going to take a sample of size 1. If I take a sample of size 1, it is its own sum. So the sums that I can possibly get are 1, 2, 3, 4, 5, and 6, and I'm going to ask it to do this 1,000 times. It's giving me a normal curve, bless its heart. Okay, so I'm going to take 1,000 samples of size 1. That means I'm just going to draw 1,000 times from this box. I'm going to do nothing to them. I'm just going to draw 1,000 times from that box. And my histogram is going to be on 1 through 6. I'm going to give it 6 bins, and if I hit return, aha. That's what I got on my 1,000 draws. Each of those values came up about 1/6 of the time. No big surprise. But that's not what I'm doing. I'm sampling 200 times and looking at the sample sum. So what this program does is it does that experiment over and over and over again. And I'm going to ask it to do it 1,000 times, and now my variable, aha. Let's take a look. Average of the box, SD of the box, we round it to 1.71. Expected value of the sum, that's our 700. Standard error for the sum, that's our 24. And what we're going to have to do is we're going to run this experiment over and over again. So the experiment is roll 200 times, take the sum, and then do that 1,000 times. I want to be a little bit careful. The variable is 700 plus or minus 24. I'm going to give myself about 200 bins. 100 on either side of 700, and if I am brave enough to hit return, these are the values that it actually got. So what it did was it made a list of 1,000 numbers. Each of the numbers is obtained by drawing 200 times from here with replacement and adding up. And that distribution is awfully close to normal. And if we asked it to do it 5,000 times, I wonder if it will. Look at that. Almost indistinguishable from the normal curve. So if you run this experiment over and over and over again, the actual values that you get tend to look normal, which is another way of saying, because of long-run frequencies, the probability distribution for the sum of 200 rolls of a die is roughly normal. And this is the reason that our normal approximations were justified. So let us see if we can actually see whether our normal approximations are justified. So we wanted the area from, what was it? It was 700 plus or minus 24. So 676 to 724. What did we say it was? Do you remember? We said 68%. Well, yeah, normal approximation, 68%, not so bad. And the actual values that were obtained in this realization of this experiment were pretty close to 68%. The approximation is really, really not bad. And this is a specific instance of something general. It doesn't matter that you started with the die. I am going to play a game where I'm going to start with something a little more strange. One, another one, another one. Oh, let me branch out. 3 and get real wild and crazy with an 8. Right, so clear all this out. And I'm going to look at one draw from this box. And, well, we'll try it 5,000 times, and I'm going to give myself, well, there are 3 values here. Why don't I give myself bins from 1 to 10, let's see. So this says there are 6 values here, 4 of which are 1s. So 4/6 of the time, 2/3 of the times, I should see a 1. And then 1/6 of the time a 3, and 1/6 of the time an 8. That's exactly what I'm saying. And it's valiantly giving me a normal curve. Yeah, we're going to pat this normal curve on the head and tell it to go away because its services are not required. On the other hand, if we sample, say, oh, why not, 200 times from here, and look at the sample sum, and do that 5,000 times, let's give ourselves a few bins here. So how do I figure out how many bins to have? Well, the expected sum is 500, give or take 36. I'll give myself a couple of 100 bins, why not? And there you have it. The probabilities are centered at the expected sum. The average of the box is 2.5. I am drawing 200 times, so the expected sum is 500. SD of the box is 2.5 and a bit by just straight calculation. There is no magic there. Times the square root of 200, and that is 36 and a bit. And so the smooth curve is the normal curve, and the histogram is the actual realization of 5,000 repetitions of the experiment. Pull from this 200 times and add up the numbers. And so you can see that the normal approximation is not restricted to coins, it's not restricted to dice. I just made that thing up on the fly, and there we've got the normal approximation for that as well. Let's see what happens if I drop the number of trials. If I drop the number of trials and give myself 50 bins, what happens? You see, you've got a normal curve, and your realizations they're getting there, they're normal-ish. They're not perfect though. It's better with more trials. Better with more trials. You've got a limit theorem. That's what you've got. And you've got the best of all limit theorems in the subject. And that theorem is called the central limit theorem. Central because it is the heart of the subject, which says that if you have any box at all and you take the sum of a large number of draws from that box, then probabilities for that sum are roughly normal. It doesn't matter how awful the box was that you started with, as long as you draw a large number of times with replacement and add up the draws. Probabilities for the sum are going to be roughly normal. No, there is no way I can prove that in stat 2x. But it's true, and it is phenomenal, and when we do statistical inference you will see its real value. Those of you who like a little bit of mathematics, the statement in math language, and even here it is a bit rough. So you've got n random variables which are independent and identically distributed. That is what happens when you draw with replacement from the same box. Each has expected value mu and standard error sigma, and you look at the sum of all of them. Then for large n, the distribution of the sum is approximately normal, and here I've given you a little more information. Which normal? The mean number of draws times the average of the box, and SD square root number of draws times the SD of the box. And the key is approximately normal, the sum, regardless of what you started with. And that's going to be really, really important when what you're starting with is a population that you don't know at all, and what you're staring at is a sample. The fact that sample averages and sample sums are roughly normal regardless of the population is going to be crucial to being able to do statistical inference. And they're also pretty handy for doing some straightforward approximations before we get to inference. And I will take an example, which is you've got a random sample of 100 people, and I'm imagining their weights, the weights of these people, to be like independent draws from a box whose average is 170 pounds and SD is 15 pounds. In other words, I've got a large population and with an average of 170 pounds and an SD of 15 pounds, and I'm drawing 100 people at random. And I'm looking at the chance that the total weight of the sampled people exceeds a certain amount. And once you've had the chance to look at that question and wonder why on earth we would be interested, who cares? Who cares about the total weight of a random group of people? Yep, people that make elevators, lifts, people that make aeroplanes, people that make stadiums, they are very, very interested in the total weight of a random group of people. And so that's what I'm going to do. I'm going to look at that, and what am I starting with? I don't know much of anything about the population that they're coming from other than their average is 170 and the SD is 15. And I can now say, all right, so I've got the sum of 100 draws with replacement from this population. What do I expect the sum to be? Well, number of draws times the average of the box. I expect it to be 17,000 pounds, the total. Give or take, standard error of the total, so standard error of the sum, root number of draws times the SD, which is 150 pounds. Great. So I expect 17,000, give or take 150. What's my problem? To find the chance that it exceeds 17,250. And what am I going to use? This is the sum of 100 drawers from a box. I am going to use the normal approximation. So how do I use the normal approximation? Well, I look at the number that's at the edge of my region and I convert it to standard units. I know how to do that. Value minus center divided by spread. And that's 1 2/3. And so what I want is the area under the normal curve to the right of 1 2/3, and that's just under 5%, and I'm done. And that's a very easy method for finding a chance that would otherwise be quite complicated. When you've come a long way from that little addition rule and that little multiplication rule, you can now find some quite complex probabilities, granted that you believe the central limit theorem. And if you go back and use that toy in your online textbook, you can do your worst with the underlying box, and as you increase the number of trials, the probability distribution for the sum will turn out to be roughly normal. This is a magic theorem, and it makes the entire subject possible.